Our final speaker in this afternoon's session is Arnold Wilkins, who is Professor Emeritus at the University of Essex, and he'll be presenting his paper, The Characteristics of Natural Images Help Predict Discomfort.
Thank you very much. Thank you for the invitation. It was Peter Boyce who pointed out to me that until recently all the work on visual discomfort has been a reaction to complaints. But I want to take a different view of Charles Darwin from that which Mark Ray alluded to just earlier. I want to talk a bit about the fact that ask the question, well, what has the visual system evolved to process? Obviously, it's images from nature, natural images. And if we consider for a moment what natural images have, they have very little flicker. In a natural image, you'll see flicker from reflections off the surface of water, from interruption of sunlight through trees. That's about all. They have a 1/f Fourier amplitude spectrum, about which more anon, which characterizes the image that the eye is used to processing. They have a very low, relatively speaking, color contrast. And what I want to show you is that in all three respects, unnatural equals uncomfortable. Flicker. If it's obvious, it's bad for you. The red line shows you the proportion of patients with photosensitive epilepsy who are liable to a seizure from flicker. And the background shows you the electrophysiology that results. The green line, superimposed, is the number of illusions of colour that normal observers will see in flicker. And the blue line is the perceptibility of the flicker. You'll notice all three curves overlap. Unfortunately, you go into the gents where I work, and compact fluorescent lamps are turned on by an occupancy sensor and produce flicker at maximally epileptogenic frequencies. This needs to be avoided. Flicker from computer screens. Some computer screens are backlit with 60 Hertz, which is well within the epileptogenic range. But there's flicker you can't see as well. Flicker from fluorescent lamps is not usually seen, but it's resolved by the human retina. It causes phase lock firing in the catnal nucleus. It interferes with human eye movement control. It causes eye strain and headaches. It increases anxiety, probably, and it impairs visual performance. We've known that for a long time. We've known it for 20 years, but unfortunately 80%, in a recent survey, 80% of schools in the UK are still lit with lighting that flickers in this way. And most computer screens are backlit with frequencies that are only slightly higher. So why does flicker that you can't see adversely affect you? Well, I think there's a simple answer. The simple answer is that you can in fact see it, although you may not be aware of it. You can see it during a rapid eye movement or a saccade. Now, critical flicker fusion ignores saccades. It's measured by observing diffuse flickering fields to remove the effect of eye movement, and it's generally measured during quotes, steady unquotes fixation without large saccades. It doesn't exist, as I'll show you. Now, it doesn't exist during natural viewing, and during natural viewing we make 2 or 3 saccades every second, and some of these eye movements are large, and when they're large, they're very fast. They can be up to 700 degrees a second. Now that produces a pattern on the retina, known as the phantom array. You get these intrasaccadic perception of patterns because the light is on at different, when the retina is in a different place in space, as it were. And this is by far the most ubiquitous temporal light artifact, far more so than the stroboscopic effect, that has been intensively studied. The stroboscopic effect requires a moving object in the field of view. The phantom array doesn't. And it's the least understood of the temporal light artifacts. So if we look at an indoor scene, before a saccade, it's in a stable image. During the saccade, there's a rapid smear. And after the saccade, the eye it receives a slightly different image. And I want to concentrate on that smear in the middle. Imagine you're in a high-speed train. You look out the window. Before the saccade, there's a smear. During the saccade, if you make a saccade in the direction the train is going, you'll actually be able to see the name of the station as you fly through, because you can see perfectly well during the saccade. But what you see and what you see before and what you see after masks what you see during the saccade. Now, the people have tested contrast processing during the saccade, and it's almost normal. So you can see perfectly well when the eye is in flight under the right circumstances. So, just to repeat, during steady illumination we have a continuous smear, and during flicker we have multiple discrete superimposed images. And sometimes those break through, as in the case of LED lighting on the back of cars, but also in other circumstances. And what I want to show you now is that the circumstances where people have complained of lighting are generally those where a phantom array is in principle visible. Now, the phantom array produces a pattern, and we ought to be able to estimate how visible that pattern is from the minimum spatial frequency that's produced by the light as the retina moves, and the number of contours and the superposition of those. Because we have a contrast sensitivity function that's non-monotonic. It peaks at about 3 cycles per degree and rolls off. We can see patterns with a spatial frequency of about somewhere between 40 and 60 cycles per degree, depending on age. So we demonstrated that first of all with this simple little experiment. This is the experiment. You look from the left target to the right target, and when you do, the image, which is the bulb, which is flickering, becomes a spatial pattern that you can see. Now, and we're going to show you that when the flicker has parameters associated with long-standing complaints, the phantom array is potentially visible. Here are some functions that we obtained. There are 2 alternative forced choice judgments. So people had to say whether the light was flickering or not, and it was either flickering or not. So 50% is chance. Excuse me. And as the contrast of the flicker increases, so the likelihood of seeing the phantom array increases with it. This is a curve for 120 Hertz for our American cousins, and this is a curve for Europeans. And you'll notice that the phantom array is not visible down here. It is visible up here. This is where tungsten lighting is. This is where fluorescent lighting is. Now, the next point I want to make about the phantom array is that it should be, in principle, most visible at about 1,000 Hertz. Not at 100 Hertz, not at 300, but at 1,000. I'll tell you why in a minute. But these data show you that as you increase the contrast, so the likelihood of seeing the phantom array goes up, and it gets easier to see at 300 Hertz than it is at 100 Hertz, which is curious. You'd expect it to get worse and worse, but it doesn't. It gets better and better. You can see it better at higher frequencies than at low. And that's because the contrast sensitivity function I showed you is non-monotonic. It reaches a peak at about 3 cycles per degree. Now, this has consequences for IEEE 1789, incidentally, because we didn't know this at the time, and so we just assumed it was an increasing monotonic function. But never mind. Now, the sensitivity is greater than 300 Hertz than 100 Hertz because, I think, the spatial frequency of the phantom array is then closer to the peak of the contrast sensitivity function. So for a 10-degree saccade, the phantom array can be seen most readily at about a kilohertz, one should think, and the putative upper temporal frequency limit for a 10-degree saccade is then 10 kilohertz. So what I'm going to show you now is that you can, in fact, see 10 kilohertz. Well, at least some people can. That's because the upper spatial frequency limit of the contrast sensitivity function is about a factor of 10 above the peak. Okay, so let's look at the effects of the frequency of the target on the phantom array. And the experiment we did was, and this is important, very unnatural. We had two fixation points, one on either side, to produce a fairly large saccade, and we had a very bright but very narrow target. Very narrow so as to produce a high spatial frequency pattern without superposition of each target. And that, I think, is key. Target was only 2 minutes of arc wide. It had a luminance of 10 to the 4 candelas. One LED, basically. So, therefore, when the phantom array has a 50% duty cycle, putatively, the spatial frequency will be about 26 cycles per degree, which is just within the limits of what's visible under continuous viewing by people who are aged less than 50. And this is what we found. 14 young observers, 2 alternative forced choice. They're able to see the threshold for the group is 6.4 kilohertz. That is, they can discriminate a pattern produced by flicker at 6,470 hertz. There's the chance value. Now, that's for the group as a whole. But there were huge differences between observers. 2 of them are doing quite well at 10 kilohertz, above chance. So, under the appropriate circumstances, and there's nothing to prevent you seeing a phantom array at very, very high temporal frequencies. Now, this is partly probably due to eye movement velocity differences. These are data from Kang. But in our data, there's a weak relationship between the discomfort people generally experience, as reported in a discomfort questionnaire, and their flicker frequency threshold measured in this way. So that was a weak relationship. We obviously got to collect more data. So the consequences for health? Well, the visibility of the phantom array occurs with flicker that has parameters associated with long-standing complaints, and the phantom array introduces a spatial periodicity. Now, we know that's important for reading because the stripes within words affect reading. 2 papers here. What they do is, if you have a word like mum, for example, and you measure the horizontal autocorrelation, as I'm doing here, you'll see that mum has a very high spatial periodicity, dad doesn't. And now, the intriguing thing is, if we just measure the first peak in the horizontal autocorrelation, you find that it predicts the speed with which that word is read. So words with a high horizontal autocorrelation, stripy words, are read 10% more slowly because the eyes take longer to realign after each saccade. Now that means that the phantom array has the potential, in principle, to affect reading, to affect the control of vergence subsequent to each saccade. Don't know if it does, but at least it has the potential to do that. So the take-home message is flicker can be bad for you, even if you can't see it. It's worse if you can. And some of the known detrimental effects of flicker are probably due to intrasaccadic perception, and intrasaccadic perception of spatial arrays has the potential, at any rate, to disrupt reading. Okay, that's flicker. Now let's move on to the power spectrum. We evolved to see jungles, all right, but not this, or this, or this. Natural images have very little spatial periodicity at any one scale. You can measure the spatial periodicity using the Fourier transform, and we find that at low spatial frequencies we have a high amplitude, and high spatial frequencies a low amplitude, and in general there's a very simple relationship of 1 upon f between amplitude and spatial frequency. So we can characterize what is natural about an image mathematically. If we just transform that to a log, we've got a straight line effectively. And if we deal with that straight line in 2 dimensions, we can fit a cone to the 2-dimensional Fourier transform to allow for differences in meridional anisotropy and differences in the fact that patterns that are unidimensional are worse than patterns that are in more than 1 dimension. Anyway, leave that aside. If we just fit a cone and we weight the residuals to the cone by a contrast sensitivity function gleaned from the literature with no free parameters at all in the model, we can predict 25% of the variance in people's judgments of how uncomfortable an image is to look at. So now we have an algorithm that's based on first principles alone that can predict people's ratings of discomfort from images. Now, what's the most unnatural image according to this model? Watch out. Those of you who are male and old needn't worry so much. Those who are young and female might wish to. And anyone who has migraine, I suggest they cover the one eye. Right, that's the worst possible pattern. And unfortunately, there it is. Sorry guys, but it's so important to avoid spatial periodicity in luminaires. It really is. So, in general, if you survey the literature, 2 interesting things emerge. Images that are uncomfortable to look at give a greater blood oxygenation of the visual cortex. That's 6 studies that have used bold and various other techniques. Plus, people who are particularly susceptible to discomfort generally tend to have greater blood oxygenation. So we've got this relationship both from differences between people and differences between images. So I think it's there. It's crossed 6, 7 studies. I'm just going to show you one study. Here we went to London, Norwich, Cambridge, and various other places, stood at the side of a curb, aimed a camera without posing it, and took a photograph of the building opposite. Urban scenes. And the model that I've just mentioned by Olivier Panucci, who was the mathematician who did it, correlated 0.6 with the ratings of discomfort in these images, and 0.5 in a replication. So it's working. And what's interesting, though, was that we measured the blood oxygenation using near-infrared spectroscopy. This is deoxygenated blood, oxygenated blood. You can measure the change in colour of the brain using infrared light. In fact, the technique was developed just next door. These are the images that people sat watching, and these are the results we got. The upper curve is for images that the algorithm thought should be uncomfortable. The lower curve is for the images that the algorithm thought should be more comfortable, divided about the median. And just if you want to look at the images, these are the ones that the algorithm have found uncomfortable. You can see they have a spatial periodicity. A spatial periodicity that's extremely common in our modern urban environment. You cannot get away from stripes. I mean, I could just point them out here. I mean, there are stripes everywhere. Don't replicate them in the lighting. That's my message. Okay, so if we move on. We just also showed in that study that photographs were a good substitute for the real scenes. That's reported here in landscape and urban planning, which is not the sort of place you normally find these studies. But anyway, the take-home message is that spatial periodicity can be measured by the Fourier amplitude spectrum in terms of departures from 1 upon f. The excess amplitude near 3 cycles per t predicts discomfort, and the spatial disposition of luminaires on the ceiling has the potential to be uncomfortable, quite irrespective of other considerations. Right, I've got a few minutes left, so we'll come to colour. Now, I have very little data on colour. What I have is a bit interesting, I hope. Is this comfortable to look at? Some children have to look at this sort of thing the whole time. Let me just show you what happens when I just slightly reduce their colour contrast. Are you ready? Now, which of those two was more comfortable, do you suppose? The second? Well, I hope so. Notwithstanding cultural differences that Mark mentioned, I think generally speaking, high colour contrast, which is very common on videos, particularly for children, can be uncomfortable. I'll just demonstrate that to you now. Here's a small colour difference. You can see the stripes perfectly easily. They're reasonably comfortable. Now, if we take a large colour difference, watch out. Oi. And if we take it doesn't really matter which colour differences you do. Are you ready? Watch out. Disgusting. Okay? Now, they are awful, at least they are to me. Some of you will find them, what a fuss about, but about 10% of the population say, what's the fuss about? The rest of us don't like them. Now, these are not due to differences in accommodation. You can accommodate, you can see, focus on these images perfectly well. What have I done? Oh dear. I need.
Don't take it anymore.
What happened?
I'm confused with the stripes.
Yeah, I've obviously killed the system.
Just a cheap meltdown.
Right, well, to cut a long story short, it is nearly time. Do you know what happened? Please wait for the projector to cool down. I've obviously killed it. Okay, well, what I was going to show you was a little video of Peppa Pig. Peppa Pig were used because the colours are nice and easy to measure. We measured them, we reduced the colour contrast, and we were able to demonstrate that adults, at any rate, found the slightly reduced colours more comfortable. So basically the message is there's a lot of very high, unnecessarily high colour contrast, particularly for children, particularly in material they're required to look at. It's unnecessarily high, it may be uncomfortable. I think that's more or less it. It certainly seems to be as far as we can. Thank you.